Okay. Good morning, everyone. So today, good morning. First of all, I'm Allan Cantle, and I'm the, wait a minute, sorry. I'm the technical lead for the OCP High Performance Compute SubProject. And today I'd like to give you progress toward an open and sustainable energy-centric computing architecture for today's AI and HPC applications. So, as a quick overview, I've already given quite a detailed overview on the high-performance compute module that we'll be talking about today at the OCP Global Summit. So if you enjoy what you see here, I'd recommend you watch that presentation. It'll give you more detail on the module that I can't really cover at the moment. But we're going to focus on efficient power delivery mechanisms in this modular approach, some thermal management concept, including energy reuse, and a universal topology interconnect for connecting all these modules together. And I'll finally give you a summary. But before we get started, for those of you that have been following NVIDIA and their latest Blackwell announcements at GTC just a few weeks ago, you will see their Blackwell implementation. And I wanted to just take a quick look at this so you can see the power, thermal, and interconnect challenges of today's AI racks. So first of all, this is the pictures of the Blackwell implementation. On the left, we see they've got a complex hybrid cooling. It actually blind mates the rack into the chassis, and you have a water-cooled plate cooling the main big devices, but it's also got the fans still in the system for air cooling as well as the water cooling. Then if we take a look at the power, this is a whopping 120 kilowatt rack, and you have power supplies from facilities power down to 48 volts at the top and the bottom of the rack, driving a bus bar like OCP Rack V3, and then on every single node, you see a cable going from the 48-volt bus bar all the way to the front of the server, through a power distribution unit, and then back to the point of load devices driving the chips. That's approximately 2.5 or up to 2.5 meters of distance between facility power and point of load, which is a lot of distance for copper losses. Then if we look at the signal integrity of our communications, we've gone away from PCB traces to cables. And so you can see on the left in the Blackwell server box, you've got cables going from the Grace CPU to the NIC cards, the InfiniBand cards in the front of the server. And on the right-hand side, the NVLink switch 1U box, we've actually got cables coming right up to the chips, right next to them, and connecting that to the backplane that then runs up and down the rack. So the motherboards have been removed completely. We don't need motherboards anymore. So, this, in a lot of ways, is quite a messy implementation in my view, and it shows we're long overdue a major need for change, and this is what we've been working on for the last 3 years in concept forming the OCP HPC, as we saw these issues coming, and we decided that we could work on solving them. So, we've got what we call a composable high-performance compute solution, with the OCP, what we're calling a wall of compute. So to take a starting point, if you're familiar with the Frontier supercomputer footprint, that is a map of the data center. Essentially, it's made up of 50,000 or approximately 50,000 CPUs, GPUs, and switches. And also there's the storage. The storage is actually separate to the actual main compute. In our implementation, we would have this wall of compute, and we would have about 50,000 HPCMs, high-performance compute modules, where the high-performance compute modules could be CPUs, GPUs, or switches. And there's just one sort of amplified away from the walls that you see there. So that's a configuration. So we've got rid of the 19-inch racks. Taking this particular look at AI and other issues, AI has got this insatiable need for memory bandwidth and capacity at low latency. We know we've got HBM giving us some capacity, but it's nowhere near enough for the AI. We're growing it at an alarming rate. If you look at NVIDIA's Grace Hopper, you see they've added a terabyte to their Grace with high bandwidth to the GPUs. but there's still not enough memory for this ever-growing need. So what we need to do is we need to get at the data. We need to bring the data much more closer to the compute. But in a classic data center, in a classic HPC, the storage is separate. The memory is separate, a lot of the big memory. And we've got 50 picojoules per bit or more to actually move that data over a relatively thin pipe. If we fatten those pipes, that power gets really big, really quick. So one of the fundamental differences of our architecture is we've coupled, or we've given the ability to couple the compute with the storage and the memory, and in a 1 to 2 picojoule per bit. So 1 to 2 orders of magnitude improvement in that power coupling there with this architectural approach. Taking a closer look at this HPCM module, it's roughly the size of an EU brick. So all in all, it's just another brick in the wall. For those of you know. So basically, it's a composable, domain-specific architecture building block. It's inspired by the OAM module, the OCP accelerator module, and you can configure this module with any processor accelerator switch up to around about 1 kilowatt. It also supports 16 E3.S modules, memory modules or media modules. It has direct water cooling. There is no air cooling in this design, with a focus on energy reuse capabilities. It also has 8 universal topology interconnects that allow you to configure any topology between the HPCM nodes. And it's called a universal topology because it can support just about any protocol, and we can actually support migration from passive copper through active copper, active optical cables, and to co-packaged optics. It's thinking about our progress towards co-packaged optics. We don't believe you can do just one breaker switch from copper to co-packaged optics, really. So that was a supercomputer, but really we're looking from high-performance computing all the way to the edge and being composable in that way. So I've just got a ChatGPT to do a Lisbon street with a telecom box on the side, and just showing a 6x6 array of high-performance compute modules in a telecom box on the side of the street. So we've got edge computing with exactly the same hardware is the concept. Power would come from under the street, and the reuse water could go into a city heat network. For example, my hometown of Bristol, UK, has a Bristol city heat network where the hot water feeds in between the buildings. Additionally, we could take maybe just a handful of modules and actually integrate them into the design of our homes, so that you could plumb that hot water into the HVAC or your hot water system and actually provide that, and then populate. Then people in their homes could buy their gaming HPCM and plug it into their utility feature in their home. I think this is very relevant. I've got some friends with teenage boys. They've just spent thousands of dollars on a gaming PC, and it's almost a kilowatt of power, and their bedrooms are boiling with the intense heat that they get. So thinking about our getting planning permission, I think this is where Europe can do far better than the US, is we should be thinking about integrating this into our homes. So that's the composability feature of it. Focusing on efficient power delivery now, just to remind you back to the NVIDIA Blackwell, we said that we had up to 2.5 meters of distance between facility power and the point of loads of the Blackwell chips. With our design, you can see in the bottom right, the facility power is in that wall of compute through a 48-volt power step down, and only literally a couple of inches, or less than 0.2 meters, between the facility power and the point of load for any one module. So we've got lower cost potential with less usage of copper, and potentially a lot higher efficiency as well, because there's less drop across the connection. Looking at the thermal management side, we've got really quite a complex, crazy idea here that I want to emphasize right at the beginning. This is completely unproven. It's a hypothetical concept, and part of the reason for presenting this is we want all of you thermal experts to be able to tell us where we're going wrong on this. But let me try and explain. So in the middle of the diagram on the right, you're actually seeing the high-performance compute module thermal elements, the water passes into that picture on the left, and that gives us a conductive cooling path for the pluggable media and the pluggable active cables. So we actually conductively cool those devices. And then the water passes up to the top of the module into what we call a mini immersion cooled chamber to cool the kilowatt processor. But we want to eject every module. We want to eject 65 degrees C or thereabouts for energy reuse purposes. So we have a control loop to control the flow depending on the power being burnt in each individual module. We then step and repeat that 8 times, because in a column, in the wall of compute, in a column we have 8 modules. And then we have a heat exchanger at the top of that column to take us to the facility water. And again, we have a similar control loop on the facility water to get the higher temperature out of the facility water. And then finally, we actually pull a vacuum of around 0.2 bar using a liquid ring vacuum pump, is the idea, to give us a 2-phase inner loop with water, where I'm reliably informed that at about 0.2 bar, you're roughly in the 60 to 65 degrees C water boiling point. And apparently that's in the order of 11 times more efficient versus single phase. On the module itself, we also have this conformally coated. So we actually insulate the electronics in the module and then conformally coat with copper on top of that. This is the University of Illinois research that they've been doing. So that gives you that sealed immersion chamber. There are alternatives, but this could be an efficient way, and it's 7 times more power per unit volume of copper efficient than traditional approaches with thermal grease. And also, by using water, we're 4 times to 9 times better thermal conductivity than PAO or Florinut. So I know this equation is too simplistic, but if you put those 3 together, in all things being equal, in theory, we could maybe get up to 300 times improvement over conventional liquid cooling. That sounds a bit ambitious, but I don't think we need that much anyway. So that's the concept. We'd love to discuss that with experts on how to turn this into a POC reality. But just to look on the water side of things, we've obviously been identified that water use concerns are big. It's electrically conductive. I mentioned the conformal coating, which should isolate us. We've got this bacterial growth challenge. We understand that stagnant water areas cause a big problem, so could we design this to eliminate the stagnant water areas? Will the water temperature, I understand the water temperature of today's liquid is in a beautiful range for bacteria to grow aggressively. And so will the hotter water improve that, or will it just shift to different bacteria? And so will the water temperature help? Clearly, we've got the corrosion issues in mix of materials causes that, so we need to be careful in the design with the mix of materials. And obviously, there's this water treatment approach, but that will reduce thermal conductivity. And with our passion to drive sustainability, it adds additional sustainability concerns. So ideally, we'd like to just stick with the water, if at all possible, and that'd be super low cost. So that's the thermal management concept. You can see that it's a very complex 3-layer control loop going on here. So moving on to the Universal Topology Interconnect, basically what we've got here is those 8 connectors on the side of the module allow us to connect the modules in any configuration that our application may desire. So again, play into this domain-specific architecture capability. We don't want to completely reinvent the wheel, so we're leveraging, at the moment, our plan of record is to leverage the PCI SIG MCIO connector. And we want to be protocol agnostic, so we can support PCIe, CXL, NVLink, HDMI, all of the different communication standards is where we want to take this to. So it's just mechanical and electrical that we're focused on. We're supporting 8 transceiver lanes natively from 32 gig all the way up to the 224 gig is where we want to support. And from a sideband perspective, we want to move from the 70s to today with using the OCP tunneling over LTPI, add some clocks, and just a single cable present static pin. But we also want to support active cable options. So we need to bring power onto the module. So on the right, I've shown the paddle card with today's active PCIe retimer chip on board, so we can put that into it. But that's a few watts, and on the right side of that diagram, you can see we've got a thermal path to that water manifold for actually cooling the active part without having to use these big QSFP and OSFP cages. Looking at an active optical solution, a company called Avicenna has an LED optical solution called Light Bundle. So that's their chip on the right. And this is just showing an animation populating that and flipping it through a hole in the paddle card on the module. If we flip that over, we can actually see that you can see the optics, the optic area coming through. We have a ferrule to actually do the mating, and then you can mate the passive optical cable. And if we zoom in on a co-packaged optics, this is where we can get the bandwidth all the way up to 8 terabytes per second on a module, which is in the order of HBM bandwidth, or even higher than HBM bandwidths today, from module to module. That would be impressive. That's using this 4 light bundles. You can see the Avicenna chips just populated directly over where the connector area would be. It's on the same size as a chip, so you have potentially chiplet interfaces between the light bundle and the processing chips. If we flip that board over and zoom in, you can see the 4 light bundle chips being visible through the interconnect, and that's in there 1 terabit transmit and receive, giving you a total of 8 terabits per connector, or 1 terabyte per connector. 8 connectors gives you the 8 terabytes per second of off-module bandwidth. And this is just showing the 4 coupling of the light fibers into that connector. They would be packaged into 1 cable connector to plug in there. So in summary, you can probably guess we've got pretty bold ambitions to bring our open computing architectures into the 21st century, and actually thinking about the challenges that NVIDIA are clearly facing with Blackwell from the ground up by redefining computing architecture from the ground up. We're really focused on a sustainable energy-centric computing first mindset, and it's really core to our vision. It requires innovations and collaboration across all of our industry silos. And that's the hard part, by the way, is getting everybody to realize that working together, we can come up with a far better solution. Thermal management is a major challenge, and we have some crazy ideas, and we'd love all the support we can possibly get, and if we can get some funding and make a POC out of this and see if it's even viable, it would be great. And AI and HPC, we know, requires system I/O bandwidth to skyrocket, and we really need to plan for this a long way ahead. So we've got revolutionary change, really does require open collaboration, and that's where I'd like to really thank OCP for giving me the opportunity to be doing this over the last few years. And finally, just as a call to action, we do need broad industry cross-discipline collaboration across all of the skills, and if you can come and join us, that would be great. Help us convert this thermal management concept into reality. Help us realize a universal interconnect that supports an evolving I/O landscape. And I've given all the details of our work group there if you'd like to come and join us. Thank you very much for your time. I'll take any questions.
We have a few minutes for questions if you guys have any.
Very bold, Allan, yeah. There's a lot of questions, actually, but I don't know where to begin, really, but the power delivery, for example, I mean, do we need to calculate how much heat generation that's going to generate? And
the power itself?
Yeah, because, I mean, looking at the 120 kilowatts at 48 volts with the tube for the Blackwell, it's something like 1,200 amps of current.
Yes.
Yeah.
So our module, the design there is the wall itself has a 48 volt facility powered a 48 volt power supply in it.
Yeah.
So we were thinking of that conductively cooling to the cold water feed of the wall itself. So in terms of managing the thermal side of that. Then the pins, the blind mate of when you plug the module in, each module is about 1.5 kilowatts, but it could go up to about 3 kilowatts because we support 72 amps in that Molex interconnect between the wall and the module. So therefore, the module is capable of going up to that. And then the cooling of the power, the point of load, is all part of that immersion cooling setup. And there's a couple of ways we can do that. We can do different lids for more traditional water cooling as well, if we needed to. But the immersion one is what we'd like to go for. Does that answer the question?
Yeah, okay, yeah. It's, can I ask another question? Yeah. Or is it, there's anybody else? Yeah, I want to ask a question, yeah.
Hi, Allan. Great talk. I was going to say, so all of this for HPC, would it also apply for AI? Because what we see from the hyperscalers, it's a very specific architectures that are being deployed for AI. And I know in our OCP CMS work groups, we kind of cross across HPC and AI. But any thoughts on that? Like everything you said, would it just transfer over to AI deployments?
Yeah. I mean, the short answer is absolutely. Slightly longer answer, it's very heterogeneous, modular, domain-specific architecture, you know, Hennessy and Patterson. So you can configure the idea is you can configure any compute, acceleration, heterogeneous configuration. The media, the memory is right there at a low energy point compared to traditional systems. So we can do high bandwidth to lots of memory that is closely coupled. And then the networking between the modules, you can add switches is modules themselves. So essentially, any machine that's been built up to today, you could build with this wall of compute fairly easily, is the idea. So yes, we should, in AI, it was designed with AI in mind as well.
I mean, that was what my question was going to be about, because I think the problem we have with HPC is that this guy wants to do CFD. Can he do it with floating point, 4-point floating point? No, he can't.
Right.
So the problem is that we got divergence. It's very application specific.
Yes.
So for general HPC, it's not really, well, we have to be able to deal with...
Well, so then that comes down to the actual chip itself on each of the modules. So actually, I work, one of my contracts is with a company called Next Silicon that's making silicon accelerators, but paying attention to HPC that everyone's forgotten. So you would just use one of their modules if you wanted to do HPC.
Okay, so it's another brick in the wall. Is what
another brick in the wall, yeah. So
okay.
you can have any heterogeneous brick, or you can mix and match heterogeneous bricks
okay.
to suit your application.
Clever idea, yeah. Excellent.